Next topic is ideals and factorings. So ideals. Let R be a ring I be a subring of R, then I is said to be an ideal. Whenever I will say it is an ideal, then it will be both left-sided and right-sided. So two-sided of R if for all A belongs to I, R belongs to ring R, AR, comma RA. This belongs to I. So whenever I will apply the element of ring from right side, then it is right ideal, and when from left side, then it is left ideal. Next is proper ideals. An ideal I is a proper ideal of R if I is not equal to R. Whenever ideal is not equal to ring R itself, then it is called a proper ideal. Next is trivial ideal. The ideal singleton identity. This is called a trivial ideal of R. Improper ideal. The ideal R is called improper ideal of R. So trivial ideal is this identity and improper ideal is this ring R itself. Next is ideal test. Let R be a ring I is non-empty, which is a subset of ring R. This is an ideal of R if first, for all A and B belongs to I, A minus B belongs to I. Secondly, for all A belongs to I, R belongs to ring R, AR belongs to I, and RA belongs to I. Then we will say that I is an ideal of R. For examples, first, for n belongs to Z plus, NZ is an ideal in Z. Means 2Z, 3Z, 4Z, so on. These are ideals in Z. Next is principal ideal generated by A. This is important. Let R be a commutative ring with unity. A is an element from ring R. Then this generator A, Ra such that R belongs to R. This is called the principal ideal generated by A. Third, let ring R is equals to polynomial ring Rx. Polynomials whose coefficients are from R. Ideal is generator X. This is equal to X fx, where fx belongs to ring R, which is Rx. This is an ideal in Rx. Note, I is the set of all polynomials in Rx with constant term 0. Fourth example, let R is equals to Zx, I is equals to generator x comma 2. So this will be like this, x into fx plus 2 into gx, where this fx and gx belongs to polynomial ring Zx. Note, I is the set of all polynomials in Zx. With constant term even. Fifth, R is equals to C01, set of all functions whose domain is 0, 1 and codomain is real numbers. Let A belongs to closed interval 0, 1, IA. This is functions which belongs to this ring R such that FA is equals to 0. Then IA is an ideal in C01. Sixth, let R be a commutative ring with unity. A1, A2, so on till AN belongs to ring R. I is equals to A1, A2, so on till AN. This is equal to R A1 plus R2, A2, so on till Rn, An, such that R1, R2, so on till Rn. This belongs to ring R. Then I is an ideal in R. Remarks. So every ideal is a subring, but not conversely. For example, Z is a subring of rationals, means ring is our rational numbers and subring is set of integers. But this is not an ideal. What is the reason for this? If I pick an element from this integers, 1 belongs to Z, 1 by 2 belongs to rational numbers, but 1 into 1 by 2. This is like AR, na? Right ideal. This should belong to set of integers, but 1 by 2 does not belongs to set of integers, so this is not an ideal. Is this clear?
Yes, ma'am.
List all the units in the ring of Gaussian integers. So how to see units in the ring of Gaussian integers? Ring of Gaussian integers Z iota. This is equal to A plus iota B such that A comma B belongs to Z. Now A plus iota B, this belongs to Z iota, is a unit if there exists C plus iota D which belongs to Z iota such that A plus iota B into C plus iota D is equals to 1, where 1 is multiplicative identity. यही डेफिनेशन थी यूनिट की.
Yes, ma'am.
ठीक है. So अब इसको सॉल्व करने के लिए क्या कर सकते हैं? वी कैन टेक इट्स कॉन्जुगेट. सो कॉन्जुगेट विल बी A minus iota B, C minus iota D equal to 1. Now we can multiply both the equations. Multiplying equation 1 and 2, we will get A square plus B square C square plus D square is equals to 1. So this means that how I can get this product as 1? Both the quantities have to be 1. A square plus B square is equals to 1 and C square plus D square is equals to 1. So A square plus B square equal to 1. Now here there will be two possibilities. Either A is equals to plus minus 1, B is 0, or A is 0 and B is plus minus 1. This means A plus iota B is equals to plus minus 1 or plus minus iota. And similarly, C square plus D square equal to 1. This implies C is equals to plus minus 1 or D is 0. C is 0 and D is plus minus 1. So here also C plus iota D is equals to plus minus 1 or plus minus iota. Therefore, units of Z iota are प्लस माइनस 1 प्लस माइनस आयोटा. कल शायद मैंने एक जगह पे डायरेक्ट यूनिट्स लिख दिए थे, तो उसका ये रीज़न था. इस तरीके से निकालने होंगे.
ऑलवेज कॉन्जुगेट लेना है इस केस में.
हाँ, जब ये आयोटा वाले केस में तो हमेशा ही कॉन्जुगेट लेके हम इजीली निकाल पाएंगे. Try this question. Which of the following rings are integral domains? MSQ क्वेश्चन है. Rx, the ring of all polynomials in one variable with real coefficients B part MNR, C part the ring of complex analytic functions defined on the unit disk of the complex plane with pointwise addition and multiplication as the ring operations.
सी पार्ट आएगा इसमें।
व्हाट अबाउट ए पार्ट?
ए पार्ट में तो सी जीरो ऑफ द पॉलिनोमियल भी हो सकता है, मतलब पॉलिनोमियल में कोई भी वैल्यू अगर मतलब जीरो ऑफ द पॉलिनोमियल भी तो हो सकती है ना। इफ आई से -1 तो पॉलिनोमियल की वैल्यू 0 हो गई लेकिन -1 0 दी।
इसमें तो सिंपल सा ये लॉजिक है दैट इफ D is an integral domain then dx ring of polynomials is also an integral domain. ये डायरेक्ट रिजल्ट है।
अच्छा,
So R is an integral domain ना, set of real numbers. So Rx is also an integral domain. So A part is correct. In case of B part, we have discussed yesterday also, we will get zero divisors na. 0 1 0 0 1 0 0 0. So AB is equals to 0 0. This means it has zero divisors. Neither A is non-zero. Sorry, neither A is 0 nor B is 0. So it has zero divisors, so it is not an integral domain. C part. Let P is equals to ring of complex analytic functions defined on the unit disk of the complex plane सी पार्ट को तो थोड़ा होल्ड पे रखना चाहिए क्योंकि कॉम्प्लेक्स पढ़ा नहीं ना अभी हमने। आपने कैसे करा सी पार्ट?
मैंने तो डायरेक्टली यूनिट डिस्क बोला है ना, तो x प्लस एक्स स्क्वायर प्लस वाई स्क्वायर इक्वल टू 1, एक्स प्लस वाई आई आयटा वाई अगर हम जेड ले तो यूनिट डिस्क है तो जेड लेस देन इक्वल टू 1 होगा ना। तो इसमें 0 तो आएगा ही नहीं, ऐसे भी नहीं है ना, तो ये तो इंटीग्रल डोमेन होगा ही ना।
जीरो नहीं आएगा।
दैट मीन्स कि अगर हम कोई भी इसमें एडिशन में अगर हम ऐड करें 0 प्लस 0 आएटा या मल्टीप्लाई, मतलब 0 प्लस 0 आएटा होगा तभी 0 होगा, अदरवाइज नहीं होगा ना किसी से भी।
ठीक है।
जेड लेस देन इक्वल टू 1 तो पहले ही है ना, इसलिए।
यस। Now next is properties of ideal. First is intersection of any two ideals of a ring R is an ideal in R. Second, let I and J be ideals in R. First, I plus J, sum of two ideals, is given by A plus B such that A belongs to I and B belongs to J. This is again an ideal in R. Second, product of two ideals. This is given by summation I equal to 1 to n ai into bi such that ai belongs to I and bi belongs to j for all I is an ideal in R. Third, let R be a ring with unity. I be an ideal in R such that 1 belongs to I. Then R is equals to I. Proof, let R belongs to R be arbitrary element from ring R. 1 belongs to I. So by ideal property, R into 1 means R into A. This belongs to I. Left ideal. So R belongs to I. Therefore R is equals to I. So whenever R is a ring with unity, I is an ideal in R such that 1 belongs to I, means unity belongs to ideal I, then R is equals to I. Fourth, let R be a ring with unity, I be an ideal in R such that I contains a unit, then I is equals to R. Small proof for this. R is a ring with unity, I is an ideal in R such that this ideal I contains a unit, then I is equals to R. So let A belongs to I be a unit in R. This means that A inverse belongs to R. By ideal property, A into A inverse, this belongs to I. इसे हो गया ना, AR belongs to I. Here A is this A only and R is A inverse. So 1 belongs to I. Therefore I is equals to R by third property. Let M3R be the ring of all three cross three real matrices if I comma j is a subset of M3R are defined as I is equals to A, B, C, rest of the entries are 0, such that A, B, C belongs to real numbers. J is equals to A, B, C and rest of the entries are 0. A, B, C belongs to real numbers. Then A part, I is a right idle and J is a left idle. B part, I and J both are left idles. C part, I and J both are right idles. I is a left idle and J is a right idle. Try this.
इसमें आई लेफ्ट आएगा और जे राइट आएगा।
यस।
डी ऑप्शन, डी ऑप्शन।
दोबारा क्या बोला आपने? आई
लेफ्ट और जे राइट।
नहीं, उल्टे बोल दिया आपने।
ऐसे था ना कि ए आर ए बिलोंग टू आई, तो आर जो है रिंग का पार्ट है, ए जो है आइडियल का पार्ट है ना। तो इसमें आ रहा है ए आर, इफ आर ए बिलोंग टू आई देन इट इज लेफ्ट आइडियल। मतलब अगर आर लेफ्ट में होगा तो उसको लेफ्ट आइडियल बोलेंगे ना। तो मैंने क्या किया, अच्छा ए आर आ रहा था, ठीक है ठीक है। तो आई राइट आएगा और जे लेफ्ट आएगा।
यस।
फर्स्ट ऑप्शन है।
Yes, A part is correct. Simply, if you take R belongs to M3R, because our ring is M3R, 3 cross 3 matrices. So R can be of this type: alpha 1 1, alpha 1 2, alpha 1 3, alpha 2 1, alpha 2 2, alpha 2 3. First of all, I am checking for I ideal. I is ABC 0 0 0, x1 into R. So this will be A alpha 1 1 plus B alpha 2 1 plus C alpha 3 1. Rest of the entries are 0 0. A alpha 1 2 plus B alpha 2 2 plus C alpha 3 2 0 0. A alpha 1 3 plus B alpha 2 3 plus C alpha 3 3 0 0. So this clearly belongs to I. And if you will check this R into this, then this will not belong to I. So I is a right ideal but not a left ideal. And similarly, you can check for J also. When you will check, J is a left ideal. Next topic is factor rings. Let R be a ring. I be an ideal in R. R with respect to plus is an abelian group. This implies I is a normal group of R with respect to addition. So R by I. This is quotient group only, R plus I, such that R belongs to R. This is the group under addition. Defined as R plus I plus Y plus I. This will be R plus Y plus I, because by property of coset, A plus I plus B plus I. This is equal to A plus B plus I. So to give R by I a ring structure, we need to define multiplication on R by I so define multiplication on R by I as R plus I, Y plus I, this is equal to Ry plus I. Then R by I under these operations is called a factor ring, also known as quotient ring. Now some examples. Let ring R be the set of integers I is equals to nz. Then R by I, this is z by nz, x plus nz, where x belongs to z. Second, let ring R be the set of polynomials. Polynomial ring. Ideal is generator x square plus 1. Then R by I, Rx by generator x square plus 1. This is equal to ax plus b plus generator x square plus 1 such that a and b belongs to real numbers. So how we have got this? Let fx belongs to rx. Now by division algorithm, there exist Rx and Qx which belongs to polynomial ring Rx such that fx is equals to qx into x square plus 1 plus Rx, where either Rx is 0 or degree of Rx is less than 2. Means Rx will be ax plus b type. Therefore, fx is equals to qx into x square plus 1 plus ax plus b. So from here, fx plus generator of x square plus 1. This will be ax plus b plus generator x square plus 1. Because in this generator, this term will get absorbed. So that's why I have written this, that Rx by x square plus 1 generator is this type. Third example, ring is set of 2 cross 2 polynomials where entries are from integers. Ideal I, this is x, y, z, w, where these entries are from 2z. Then R by I, this is equal to a1, a2, a3, a4 plus ideal such that these AIs, these entries are from 0 or 1 because z by 2z is same as z2 and z2 contains two elements 0 and 1. for all I is equals to 1, 2, 3, 4. Now some properties of factor rings. Let R be a ring and I be an ideal in R. First, if R is commutative, then R by I is commutative. Second, if R has unity, then R by I has unity as 1 plus I. Third, let A be an ideal in R such that I is a subset of A, then A by I is an ideal in R by I. Note, if R is an integral domain, I is an ideal in R, then R by I need not be an integral domain. Means if R is an integral domain, I is an ideal in R, then factor ring need not be an integral domain. For example, let R is equals to set of integers, which is an integral domain. Ideal is 6z, so R by 6z. This will be 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, 4 plus 6z, 5 plus 6z, and when I will write 6 plus 6z, it will get absorbed in this 6z. Now 2 plus 6z is not equal to 6z. 3 plus 6z, this is also not equal to 6z. What about their product? 2 plus 6z into 3 plus 6z. So this will be 6 plus 6z. So it will get absorbed in this. 6 will get absorbed in this 6z. So we will get 6z. So this means that neither this element is 0 nor this element is 0, but then also I am getting this AB is equals to 0. R by I has 0 divisors. Let A, B, C, D be real numbers. नहीं अभी ये नहीं कर सकते. एक सेकेंड. Now next topic is ring homomorphisms. Let R and R bar be two rings. A map F from R to R bar is a ring homomorphism if F A plus B is equals to F A plus F B for all A comma B belongs to ring R. F A B is equals to F A into F B for all A comma B belongs to ring R, because ring R has two operations, addition and multiplication. So we will see that addition operation is also preserved and multiplication operation is also preserved. Next is, what is a kernel? Let F be a mapping from R to R bar, be a ring homomorphism, then kernel of the homomorphism kernel F is equals to x belongs to R such that fx is equals to 0. Also, kernel F is an ideal in R. As we have discussed in group theory also, that kernel is a subgroup of group G. Similarly, kernel F is an ideal in R. Isomorphism. A bijective ring homomorphism is an isomorphism. Means 1 on 2, and ring homomorphism is an isomorphism. Next is ideals as kernels. Let I be an ideal in ring R. Then I is the kernel of the homomorphism F is a mapping from R to R by I. Fx is equals to x plus I for all x belongs to ring R. So this ideal I is the kernel of the homomorphism. Now some examples. Let n belongs to z plus. F is a mapping from Z to Zn defined as fx is equals to x mod n for all x belongs to Z. So clearly it is a ring homomorphism. You can clearly check this now. Fx plus y, fx, fy. Fx plus y. This will be x plus y mod n, x mod n plus y mod n. So this is fx plus fy. Similarly, fxy. This will be xy mod n. This can be written as x mod n into y mod n. So this is equal to fx into fy. Therefore, f is a ring homomorphism. Second, f is a mapping from Rx polynomial rings to R defined as f gx is equals to g0 for all gx belongs to Rx. Then f is an onto ring homomorphism. And kernel of f gx belongs to Rx such that f gx is equals to 0, so such that g0 equal to 0. So this will be generator x. F is a mapping from Z to Z, which is defined as fa is equals to a for all a belongs to integers. This is an isomorphism. Fourth, let ring R be a, b, b, a, where these entries are from integers. F mapping from R to Z is defined as f a, b, b, a is equals to a minus b. F is an onto ring homomorphism. Now some properties of ring homomorphisms. Let F mapping from R to R bar be a ring homomorphism A be a subring of R and B be an ideal in R bar. So F mapping from R to R bar is a ring homomorphism. A is a subring of R. B is an ideal in R bar. First, F a to the power n. This can be written as Fa, then whole to the power n. Also Fna. This is equal to Nfa for all n belongs to integers. Second, fa is equals to fa such that a belongs to R is a subring of R bar. Third, if A is an ideal in R, F is onto, then FA is an ideal in R bar. A is an ideal in R, F is onto, then FA, image of this F under this ideal, is an ideal in R bar codomain. Fourth, F inverse B is equals to x belongs to R such that fx belongs to B is an ideal in R. Fifth, if R is commutative, then FR is also commutative. Sixth, if R has unity and R bar codomain is not equal to 0 and F is onto, then F1 is the identity of codomain, which is R bar. Now some isomorphism theorems. The isomorphism theorems. The first isomorphism theorem for rings. Let F mapping from R to R bar be a ring homomorphism then R by kernel F is isomorphic to FR. Second theorem, let A be a subring of R and B be an ideal of R, then A by A intersection B is isomorphic to A plus B by B. A is a subring of R, B is an ideal of R, then A by A intersection B is isomorphic to A plus B by B. Third isomorphism theorem. Let A and B be ideals of a ring R with B as a subset of A, then R by B upon A by B. This is isomorphic to R by B. Next is co-maximal ideals. Let R be a commutative ring I and J are proper ideals in R, then I and J are called co-maximal ideals if I plus J is equals to R. So I and J are proper ideals in R. I and J are called co-maximal ideals if their sum is equal to ring R. Next is Chinese remainder theorem for rings. Let R be a commutative ring I and J be co-maximal ideals in R, then R upon I intersection J is equals to R upon Ij, and it is isomorphic to R by I into R by J. R is a commutative ring, I and J are co-maximal ideals in R, then R upon I intersection J is equals to R upon Ij, which is isomorphic to R upon I into R upon J. ठीक है. इसके बाद नेक्स्ट टॉपिक है हमारा प्राइम आइडियल्स और मैक्सिमल आइडियल्स, वो फिर हम नेक्स्ट वाली क्लास में कर लेते हैं.
ठीक है मैम.